Okay, so we are looking at day 3 here. This is going to be our third PowerPoint where we go over the skeleton and the muscular system. So we're going to be going over your Memler's textbook chapters 7 and 8, actually. So it makes kind of a jump, right? I think it goes from like chapter 3 straight to chapter 7. So we're going to be going over a little, well, obviously we're going to talk about bones, but we're going to talk about like the different divisions of your skeletal system. We're not going to spend so much time talking about like disorders of the skeletal system. I mean, we'll certainly mention certain bits, but we definitely want to understand the joints because that's what your skeletal system is made up of. But also inside those joints, disorders, types of joints that you've got, and then any of their special structures in there as well, such as like ligaments, right? And then we'll understand a little bit about the anatomy and physiology. So I'm gonna go ahead and start us off with a little crash course video here. Let's go to YouTube here. Okay.
It's TV night, which is...
This is the one that I want? No, I want this one.
So the first time we received Home Chef, I absolutely love this. It's amazing.
Yep, I'm sure it's great. All right, here we go.
In March of 2015, American astronaut Scott Kelly and his Russian colleague Mikhail Kornienko began an unprecedented mission in space. They began a 1-year term of service aboard the International Space Station, the longest tour of duty ever served on the ISS. Now, I imagine there's all sorts of stuff to worry about when you're packing for a year-long space voyage, like, say, how many books should I bring? How many pairs of underwear? Am I really okay with pooping into a suctioned plastic bag every day for a year? Will I come upon a derelict ship haunted by some stranded an insane astronaut from a forgotten mission, like in pretty much every space horror movie ever? Will there be coffee? Reasonable questions all, but in reality, another one you might want to ask is, will I be able to walk when I get back home? We know microgravity is hard on a body, and this mission is largely about testing the physical effects of being weightless for so long. Astronauts often experience things like trouble sleeping, puffy faces, and loss of muscle mass, but perhaps the most serious damage a microgravity environment causes is to the bones. And bones, well, they're pretty clutch. So they may look all dried up and austere. Don't be fooled. Your bones are alive. Alive, I tell you. They're actually as dynamic as any of your organs and are made of active connective tissue that's constantly breaking down, regenerating, and repairing itself throughout your lifetime. In fact, you basically get a whole new skeleton every 7 to 10 years. In short, your bones do way more than just providing your squishy sack of flesh with support and scaffolding and the ability to move around. Your bones are basically how you store the calcium, phosphate, and other minerals you need to keep neurons firing and muscles contracting. They're also crucial to hematopoiesis, or blood cell production. All of your new blood, and we're talking like 1 trillion blood cells a day, is generated in your bone marrow, which also helps store energy as fat. Bones even help maintain homeostasis by regulating blood calcium levels and producing the hormone osteocalcin, which regulates bone formation and protects against glucose intolerance and diabetes. So the big buzzkill about life in space is that up there, a person suffers 1 to 2% bone loss every month. By comparison, your average elderly person experiences 1 to 2% bone loss every year. So for Kelly and Kornienko, that could mean losing up to 20% over a year in orbit. Given everything your bones do for you, that's really serious. And while most of that loss is reversible once they're back on Earth, it's not as easy as chugging some of Madame Pomfrey's Skeletal potion. Rehabilitation can take years of hard work, and that's after just a few months in orbit, which is why Kelly and Kornienko are heroes of science, and not just for scholars of anatomy and physiology everywhere, but for anybody who has bones. An average human body contains 206 bones, ranging in shape and size from the tiny stapes of the inner ear to the huge femur of the thigh. That's a lot of bones to keep tabs on, so anatomists often divide these structures first by location into either axial or appendicular groups. As you might guess, your axial bones are found along your body's vertical axis in your skull, vertebral column, and rib cage. They're kind of like your foundation, the stuff you can't really live without. They carry your other body parts, provide skeletal support and organ protection. Your appendicular bones are pretty much everything else. The bones that make up your limbs and the things that attach those limbs to your axial skeleton, like your pelvis and shoulder blades, these are the bones that help us move around. From there, bones are generally classified by their shape, and luckily those names are pretty obvious. Long bones are your classic-looking dog bone-shaped bones, the limb bones that are longer than they are wide, like the tibia and fibula of your lower legs. but also the trio of bones that make up your fingers. Follow some of those long bones to your foot or hand, and you'll hit a cube-shaped short bone like your foot's talus and cuboid, or your wrist's lacunate and scaphoid. Your flat bones are the thinner ones like your sternum and scapulae, and also the bones that make up your brain case. And your irregular bones are all the weirdly shaped things like your vertebra and pelvis, which tend to be more specialized and unique. But despite their variations in size, shape, and finer function, all bones have a similar internal structure. They all have a dense, smooth-looking external layer of compact or cortical bone around a porous, honeycomb-looking area of spongy bone. This spongy bone tissue is made up of tiny cross-hatching supports called trabeculi that help the bone resist stress, and it's also where you typically find your bone marrow, which comes in two colors, red and yellow. Red marrow is the stuff that makes blood cells, so you should be glad that you have some of that, and yellow marrow stores energy as fat. If you happen to be a predatory animal, yellow bone marrow can be one of the best sources of calories you can find. The arrangement of these bone tissues, though, can be slightly different from one type of bone to the next. In flat, short, and irregular bones, for example, these tissues kind of look like a spongy bone sandwich on compact bone bread. But in some of your classic long bones, like the femur and humerus, the spongy bone and its red marrow are concentrated at the tips. These flared ends, or epiphyses, bookend a bone's shaft, or diaphysis, which instead of having spongy bone in the center, surrounds a hollow medullary cavity that's full of yellow marrow. Now, although bone can look rock solid, grab a microscope and you'll see that it's actually loaded with layered plates and laced with little tunnels. It's intricate and kind of confusing in there, but the more you zoom into the microanatomy of bones, the better you can see how they're built and how they function right down to the cellular level. Let's start with the basic structural units of bone called osteons. These are cylindrical weight-bearing structures that run parallel to the bone's axis. Look inside one and you'll see that they're composed of tubes inside of tubes, so that a cross-section of an osteon looks like the rings of a tree trunk. Each one of these concentric tubes or lamellae is filled with collagen fibers that run in the same direction. But if you inspect the fibers of a neighboring lamella, either on the inside or the outside of the first one, you'll see that they run in a different direction, creating an alternating pattern. This reinforced structure helps your bone resist torsion stress, which is like twisting of your bones, which they experience a lot, and I encourage you not to imagine what a torsion fracture of one of your bones might feel like. Now, bone needs nourishment like any other tissue, so running along the length of each osteon are central canals which hold nerves and blood vessels. And then tucked away between the layers of lamellae are tiny oblong spaces called lacunae. As tiny as they are, these little gaps are where the real work of your skeletal system gets done, because they house your osteocytes. These are mature bone cells that monitor and maintain your bone matrix. They're like the construction foreman of your bones, passing along commands to your skeleton's two main workhorses, the osteoblasts and the osteoclasts. Osteoblasts, from the Greek words for bone and germ, or sprout, are the bone building cells, and they're actually what construct your bones in the first place. In the embryonic phase, bone tissue generally starts off as cartilage, which provides a framework for your bones to grow on. When osteoblasts come in, they secrete a glue-like cocktail of collagen, as well as enzymes that absorb calcium phosphate and other minerals from the blood. These minerals form calcium phosphate, which crystallize on the cartilage framework, ultimately forming a bone matrix that's about 1/3 mineral, 2/3 protein. From your time in the womb until you're about 25, your osteoblasts keep laying down more collagen and more calcium phosphate until your bones are fully grown and completely hardened. So while your osteoblasts are the bone makers, your osteoclasts are the bone breakers, which is a kind of violent image. Maybe think of them as like a bone breaker downer. Although the two kinds of cells do exact opposite jobs, they're not mortal enemies. In fact, I'm happy to report that they get along fabulously and create a perfect balance that allows your bones to regenerate. It's like if you want to renovate your house, you got to rip out all those busted cabinets and the musty carpeting before you can bring in the nice hardwood floors and custom countertops. These cells work in a kind of similar way, in a process that I'd argue is less stressful than home improvement, called bone remodeling. The supervisors of this process are those osteocytes, which kick things off when they sense stress and strain or respond to mechanical stimuli, like the weightlessness of space or the impact of running on pavement. So say you're out running and something happens, nothing to be alarmed about, but suddenly the osteocytes in your femur detect a tiny microscopic fracture and initiate the remodeling process to fix it up. First, the osteocytes release chemical signals that direct osteoclasts to the site of the damage. When they get there, they secrete both a collagen-digesting enzyme and an acidic hydrogen ion mixture that dissolves the calcium phosphate, releasing its components back into the blood. This teardown process is called resorption. When the old bone tissue is cleaned out, the osteoclasts then undergo apoptosis, where they basically self-destruct before they can do any more damage. But before they auto-terminate, they use the hormone hotline to call over the osteoblasts who come in and begin rebuilding the bone. The ratio of osteoclasts to osteoblasts can vary greatly, and if you stress your bones a lot through injury, by carrying extra weight, or just normal exercise, those osteoclasts are going to be swinging their little wrecking balls nonstop, breaking down bone so it can be remade. In this way, exercising stimulates bone remodeling and ultimately bone strength. So when you're working out, you're building bone as well as muscle. Which brings us back to our two space heroes / guinea pigs, Scott Kelly and Mikhail Kornienko. Space crews generally need to exercise at least 15 hours a week to slow down the process of bone degradation, but even that can't fully stave off loss of bone density. In microgravity, osteocytes aren't getting much loading stimuli because less gravity means less weight. But for reasons that we don't understand yet, the osteoclasts actually increase their rate of bone resorption in low gravity, while the osteoblasts dial back on the bone formation. Because there's more bone breaking than bone making going on, everything is out of balance, and suddenly people start experiencing 1 to 2% monthly loss in bone mass. So in addition to providing astronauts with oxygen and water and food and protection from radiation and an environment that will keep them mentally stable, it turns out that we also have to figure out how to keep their bodies from consuming their own skeletons. But at least today we learned about the anatomy of the skeletal system, including the flat, short, and irregular bones and their individual arrangements of compact and spongy bone. We also went over the microanatomy of bones, particularly the osteons and their inner lamella. And finally, we got an introduction to the process of bone remodeling, which is carried out by crews of osteocytes, osteoblasts, and osteoclasts. Special thanks to our headmaster of learning, Thomas Frank, for his support for Crash Course and free education. And thank you to all of our Patreon patrons who make Crash Course possible through their monthly contributions. If you like Crash Course and you want to help us keep making cool new videos like this one, you can check out patreon.com/crashcourse. This episode was co-sponsored by the Midnight House Elves, Fatma Iqbal, and Roger C. Rasha. Crash Course is filmed in the Dr. Cheryl C. Kinney Crash Course studio. This episode was written by Kathleen Yale, edited by Blake DiBastino, and our consultant is Dr. Brandon Jackson. Our director is Nicholas Jenkins. The editor and script supervisor is Nicole Sweeney. Our sound designer is Michael Ronda, and the graphics team is Thought Cafe.
Okay. So, all right. So let's go ahead and, talk about all that fun stuff. All right, so our skeletal system, right? We're gonna go ahead and start off by just mentioning, and clearly defining that, right? So our skeletal system is a system made up of bones, joints, and connective tissues. So when we're talking about, the anatomy of things here, we're definitely going to talk about the bones, but we also have to talk about the structures that hold those bones together and the spacing in between them and how that spacing is shaped, because that shape kind of determines how our skeletal system moves, right? So when we're looking at our skeletal system, it's going to be divided into primarily two sections. You're going to have your axial skeleton, which is your skull, your vertebrae, and your entire rib cage. And then you have your appendicular skeleton, which is your arms and legs. And the appendicular skeleton is kind of cool. One of my favorite weird things about your appendicular skeleton is this little connection right here where your clavicle comes together and attaches to your sternum. That is the only thing that's the only hard bone connection that your appendicular skeleton has to your axial skeleton. The only structure that's actually holding that together is this little tiny joint. There's a lot of soft tissue and muscle and stuff, but that's kind of a fun. Bless you. I mean, I guess it's somewhat similar here, right? You see but your sacrum has got a lot of surface area contact. This is pretty tiny.
Yeah, it's pretty small.
So I love that. It's how can we do pull-ups, with that little tiny connection? So if we're talking about it, right, let's go ahead and quickly define what a bone is. Bones are hard tissues that act as a framework for the body, right? So that's their main kind of function. Is they're there to give our body structure. They do protect delicate structures, right? Their functions are going to be to protect delicate structures. They store calcium. They produce our red blood cells, which is hugely important. But the one that's really important to us is going to be they act as levers for the muscular system to manipulate. And that's really where we're looking at like our connection today, right? Your skeletal system is what acts as like an actual lever. If you were just a series of like muscles inside of like your skin and other stuff, we would just kind of like quiver around on the ground. We need to have like our bones to kind of act as a lever to actually move stuff. So if we're looking at like your bone structure, they mentioned this in the video, but you're going to have like your diaphyses, your different membranes, and then like different types of tissue throughout that. And you're going to have your epiphyses. So these epiphyses right here are like the ends, right? They're the knobby parts of the bone where usually they have kind of a unique shape depending on what type of like bone they are. Like there's a long bone and it's going to sit in a ball and socket joint. So you'll notice it has pretty bulbous, like round style epiphyses. The diaphyses is like the really long, like hard section in the center. And then you'll have like what are called your epiphyseal plates, which are these little plates that would be right in here. That's actually where bone growth occurs. So when your bones are growing as you get older, if you ever experience like growing pains, that was coming from like these parts of your bone right here. Okay. Yeah, and then you can see like different types of marrow within that skeletal system as well, right? So we're gonna see like here, this is very much like this kind of what we call spongy bone, right? That's where all your red marrow is at. Most of your red blood cell production happens in here. And this happens to be like your femur, this specific bone right here, where a ton of red blood cells get created. So your blood cells are constantly, what's that?
Why is that?
Why is it made in your bones?
Or no, why is it like the femur like makes so much?
Oh, because it has like it's just a really large surface area. It's a really great place to house like a network of all this. Like there's a really large section of bone. A lot of your other bones, like you might like you look at your pelvis and stuff, right? That's a really big bone too. But this is like not only it's you know, it's the same reason why this would, when you think of like a caveman with like a bone, this is why this would make such a good weapon, is because like it's got this nice, thick, heavy part here. So that's just like a really great area to produce red blood cells. Okay. But it is the responsibility of your skeletal system in general to do that. But a lot of times when you picture like femur fractures and stuff, that becomes like a thing that you need to talk about because it can cause like pretty intense and like internal hemorrhaging and things like that. Wow. So that is your red blood cell production. Now you're also going to have your white marrow in this section here, or your yellow marrow, and that is where you're going to produce your white blood cells. So your immune system's being created in here, whereas like all your nutrient delivery and oxygen delivery and things like that is going to be created in here. You can see there's blood vessels running throughout all of your bones, which always is kind of surprising when you think about it. You think about blood vessels, you think about the stuff running under the surface of your skin, but this has to run through all of these tissues in order to make sure that your bones are kept alive. So looking at it, right, and here's what that marrow kind of looks like if we do like a cross section. But if you look at like the arrangement of your bones, you'll notice they kind of come in these kind of interesting, they kind of look like the rings of a tree. But this is not how, you can't cut this in half and count how old you are. But that is arranged in what is called like an osteon. And they're in these kind of circular arrangements here because that helps your bone tissues avoid fracturing whenever they make this like twisting motion, which is going to happen all the time. I mean, if you think of like having a dumbbell in your hand and you raise your arm up overhead like this, right? Like, your bones are very much kind of like, I don't have a pencil with me, but picture like a traditional, like just #2 wooden pencil, right? Yeah. And if you grab it and you like slowly start to bend it, but you're going to go slow enough that you don't want to break it in half, there's going to be a point where you start to hear like, you're going to start to hear these little tiny fibers in the wood breaking and splintering, right? Eventually it'll just snap in half. Your bones are actually like that as well. Like every time you twist or move your bones, it creates little tiny micro fractures in this, what is called our matrix. And that bone matrix getting fractured is kind of a good thing in our industry, as long as we're controlling how much, we fracture it. Because what's going to happen is those little cells that were mentioned earlier, and we're going to get to in just a minute, are going to come along and like repair those things, right? So in your bones, you are going to have these specialized structures called your osteocytes, right? And so Oh, shoot, really quickly. Yeah, like long bone formation that happens at those epiphyseal plates. So actually, we'll do bone resorption here. So bone resorption, probably the most important part of this for our talk. Really? You don't have the, oh, I put resorption. I was like, really? Word doesn't have this word? So bone resorption is the process of breaking down old or damaged bone tissue, right? It is an important part of bone remodeling, right? So, so when you, okay, fine, you win. So when we talk about like resorption is the process of like taking your bone back. It's almost like bone reabsorption, right? That's honestly what's happening. And then your body will take that damaged tissue, break it down, and then lay down new tissue to fix it up and make it more perfect. So that's bone resorption. And there's two primary cells that are responsible for that. You have got your, which are called your osteocytes. You have got your osteoclasts, which are specialized cells responsible for resorbing old bone tissue. And again, he puts it really well in the video. They're your bone breaker downers.
Yeah.
Right? Which kind of sounds like they're the enemy here, right? Like, it's like, I'd kind of like to keep my bone.
Yeah,
like,
bone to break.
Right? Yeah, exactly. But they are really kind of a good thing. They're very, very necessary. You've also got the exact opposite of your osteoclasts, which are going to be osteoblasts. And we're not quite seeing these in the notes here real quick, but I'm going to go ahead and put them up here. So osteoblasts are specialized cells responsible for building up new bone tissue. And they are your bone builder uppers, right? So if your osteoclasts are in charge of like resorbing that old bone, the thing is like they eat away all of that calcium phosphate, right? They basically go along and they kind of chew it all up. And then they spit the remnants of that out. And so that's now kind of floating around. And luckily, your osteoblasts are coming along right afterwards. And what your osteoblasts are going to do is they're actually going to lay down, they're going to spit down this like glue-like structure full of all these different types of enzymes. And that attracts all of those ingredients from before. And then that actually builds up that new tissue. But it's nice and smooth and repaired. So whenever you create like a microfracture, that triggers an immune response where your osteoclasts come along and they fix that microfracture. But now you have like slightly compromised bones, but luckily you've got osteoblasts coming along right afterwards, and they're going to lay down a matrix that's going to make it more, they're going to fix it. But here's what's really, really, really cool and why we're talking about this. The more often you do this, and we don't 100% know why the body is triggered this way, but this is the same process that your muscles go through in order to build. Your body, rather than building things back up to where it was, it will try to build things up to make it more resistant to damage next time. So what it'll actually do is it'll lay down more, because you've also been eating calcium and phosphorus in your diet. So you've got extra calcium available now. So you're laying down the old stuff and you're bringing in some new stuff. And so you're going to have stronger, more dense bones the more often you go through this process. And that's why, like in the video, he mentions like the astronauts, they're up in space, there's no gravity weighing on their bones. And so because of that, they're not experiencing those microfractures quite as often. And without microfractures, their body has no reason to build up new bone tissue. So they're just slowly losing bone density.
Yeah.
Crazy, right?
When you dislocate something, is there any like small fractures that go on during this?
Oh, probably, yeah, on a very small level. They definitely can come together, but a dislocation is where you've removed a joint from its cavity. And so now what is much more likely is that you damaged all of the ligaments that would normally hold that bone in place.
Okay.
That's much more likely what happens, but there's no reason you couldn't like certainly create like a small microfracture on the way out.
Yeah.
But you look at like what exercise does, right? Like exercise is lifting super heavy weights against gravity. Picture that pencil I mentioned earlier that we slowly flexed, right? Now imagine you take a piece of string and you tie like a 3-pound weight to that pencil. If you hold that 3-pound weight and like it's tied to the end of the pencil, right? Like maybe like if this is the end of the pencil, you tie it right here. If you hold it here, right, that's not going to, it's putting a lot of pressure on the pencil, but luckily like where you're holding it is not meaning that there's not like a lot of pressure distributed about. But if you held it at the very end, now all that weight is bending that pencil downward, right?
Yeah.
That's the same thing that happens when you do things like lateral raises. Your muscle is just attached, it only attaches right here for the whole arm. So when you like raise it up against that, you're basically bending your bones. And so that creates microfractures, which is great because then your body's going to come along and repair it later. Your quadriceps, they insert on this little tiny bone just in the very top of your tibia, like runs down your entire thigh, and it just inserts basically right under the kneecap, like right here. There's nothing, the rest of it is a totally different muscle in charge of controlling your ankle.
Yeah.
So that's a very small point. So when you do like a leg extension or a squat, that creates torque, which is going to microfracture your skeletal system, or even just like the impact of daily walking or the impact of doing things like squat, jumps, and burpees, right?
Yeah.
And what that does is that produces more dense bone tissue slowly over time. And that's why exercise has been directly linked to bone density. And it's one of the most important things we do. A lot of times we spend most of our time talking about building up muscles in the cardiovascular system, but like keeping the skeletal system strong is a big part of what we do as well. So those are your osteoclasts. They're your they break down bone tissue, right? And your osteoblasts, they build up bone tissue. And so like that whole process is called bone remodeling. And that's something that we want to have happen all the time.
Yeah.
Now, the next thing we got to talk about is our joints, right? So joints, and I'm going to give this kind of a definition that you're not going to see here, but you're going to see it later in your NASM texts. Joints are going to be the articulations where two or more bones come together. Okay, so that's our kind of textbook definition of a joint there. So a lot of times you're going to hear the word articulation, and articulation is just basically like if I were to, you look at how my knuckles are kind of feeding into each other there, that's creating like a lot of articulation. There's a significant amount of like surface area contact, which is like a kind of a weird word, but I think it comes from like Latin or something. So we got a lot of different types of joints, right? We've got 3 kind of primary categories. But really only one of them is actually, super important to us. You're going to see fibrous joints, which are joints that have no joint cavity and are immovable. So these are really like joints that don't get me wrong, they're super important, but like they're not really a big part of our job. Like they don't move. Trainers are not interested, but like the sutures of your skull is like 7 bones all coming together. That, we kind of think of it as like one big central dome, but that's not really all that accurate. Your pelvis, actually, I think I got a picture of it coming up. Let me zoom crazy forward. No? Okay, great. We used to have a picture in here. Let's see here, sutures of the skull. If you look at your skull, you can see all the individual like bones kind of coming together here. These are fibrous joints. They're not really meant to move. You've also got like sutures in your pelvis, right? And so you can see like where the pelvis actually comes together. There's like a little division right here. So for the most part, like that's what we're talking about. Now, the other type of joint that we have are also going to be cartilaginous joints. Which is important to us, but not in the sense that like we're going to try to actively exercise these things. In fact, we're going to pay attention to these things so that we can create stability so that these don't move very much. So these are slightly joints that have no joint cavity, but do have small bits of cartilage in between. Okay, these are, oh, and actually I should put this down here. These are non-movable joints. And these, oops, these are semi-movable joints. So your cartilaginous joints can move a little bit, but for the most part, they're not really meant to. Where your two bones come together, right? We're going to call that like where your two pelvic bones come together. Does that say pelvic bones in whale? Did that okay. No. What did I Google? What did I Google in the past? So like this is a great example of a cartilaginous joint where your two pelvic bones actually come together. This is really not meant to move very much, but it is meant to, you know, it allows like a little bit of torque to happen and a little bit of like raising like this. You know, it can do a little bit of that, a little bit of that, and a little bit of twisting. But for the most part, you know, we want it to stay pretty static.
Yeah.
And then most of the joints in your body, 80% of your joints are going to be synovial joints. Actually, synovial joints are fully movable joints with a joint cavity and specialized materials inside that cavity, right? So your synovial joints have a lot of really cool stuff. They have synovial fluid. They'll often have ligaments attaching them. And so
would that be like the wrist and like your shoulder and stuff?
Yeah, absolutely. Actually, you know what? I'm going to change this slightly, but we'll say joints that have a joint cavity and synovial fluid. So these are fully movable joints. Okay. So what's great about synovial joints is that they move really well. Yeah, your wrist, your fingers, 80% of the joints in your body, everything in your neck, you know, all those movements that allow us to happen. And that's great, but the problem with having increased mobility is with decreased stability. So you happened to mention earlier, like a dislocation in the shoulder, right?
Yeah.
So the problem with the shoulder dislocation, this right here, your shoulder is the most mobile joint in your entire body. It's a ball and socket joint, which means that it can move in any type of motion that we have. So there are specific joint motions that we're going to kind of go over, right? We've got things like flexion and extension. We've got abduction and adduction. We have got like elevation and depression. We've got internal rotation. We've got external rotation. Now, some joints can only do one thing, right? Like my fingers, they can really only do like flexion and extension, right? That's really their job there. Now, they can do a little, like if I twist them, right, they can do a little bit of that. And they can do abduction and adduction a little bit as well. But really, they're primarily responsible for this and that, you know, so that I can do the Star Trek thing. But what's great about like a ball and socket joint, it can do every type of motion we've got, which is called circumduction. Circumduction is a combination of every single type of joint action happening simultaneously. So like a lasso movement, right? That's a great example of circumduction. And what's happening is like I can adjust at my shoulder to compensate for the fact that my elbow can only go like this.
Yeah.
And then I do have a little bit of rotational movement, but that's actually happening in a different joint that happens to be located in the same spot. You get, technically you get two joints in your elbow actually, which is fun. I always love saying that stupid fact. Your elbow is everybody's double jointed. That's just me being like a jerk. But you know, yeah, you've got where it articulates with your humerus and your radius, but then you've also got where your radius and your ulna come together. So those are fully movable joints, which is again really great. But they often have some other special structures as well, right? So specialized structures found. What did I do? Structures found in synovial joints are going to be things like ligaments, which are soft tissue that attaches bones to other bones. So because of their decreased stability, they have to have ligaments that hold them in place. And that's what a ligament is, right? A ligament is going to attach one bone to another bone, or maybe multiple bones. Then you are also going to have like a joint capsule, which actually I won't spend too much time with. You'll have cartilage in there, just like we had in our cartilaginous joints. So cartilage, which is like soft tissue that prevents bone-on-bone friction. When you hear of somebody who has like osteoarthritis, what that is they've just spent so much time impacting their bones over the years that they've slowly worn down their cartilage and like hyaline structures and things like that. They might have things like menisci or a meniscus on either side. So like your knee, for instance, has these two special structures called your meniscuses. Your menisci. And so when you hear somebody say they have a torn meniscus, that's these special little C-shaped things that kind of sit, they kind of look like half pipes actually.
Oh yeah.
And they kind of sit like this, and that keeps your knee from sliding out in both of these directions. If it ever slides up, it'll just kind of slide right back into place, unless you tear your meniscus off. And then you've got things like sometimes they'll have fat tissue in there. They'll have these things called fat pads. And sometimes they'll have like bursa as well. And bursa are basically these little fluid-filled sacs that are there to like make, decrease the friction as well. So here you can kind of see a lot of this, right? So you can see ligaments here, right? These are individual ligaments that are holding your femur attached to your pelvis. And then inside you can see there's a little bit of like cartilage there. And then you can't really see it, but there's, oh, I forgot to mention, there's also synovial fluid, which is a viscous, I love this definition, a viscous, is that how you spell viscous? I don't even trust it. Oh God, I'm not getting any help. Viscous material. Help me out. Yeah, it's the OUS. Basically it means slimy. It's like a slimy material that prevents friction between synovial joints. And so like it kind of actually, what's weird about synovial fluid? It actually kind of looks like egg whites. This is going to be kind of gross, but synovial fluid. You'll never forget it after you see a picture. There we go. Kind of looks like this. It's supposed to be pretty clear, but you'll see somebody whose like leg is bleeding, or maybe somebody who has like an infection, or someone who's inflamed. But generally, it's supposed to kind of look like clear egg whites for the most part, and it's really slimy, and that's a good thing. That prevents friction. So here's the knee, actually. Here's a great example of all the soft tissues. Your knee's got it all. Your knee is like this joint that has to deal with so much pressure. And so you can see like, here's actually a tendon, which is what attaches your muscles to bones. And we're gonna get to that definition later. And then here's like a special little bone. Here's your patella, which is what's called a sesamoid bone. There's a floating bone that doesn't have like a ligament attaching it to any other bones. It's just kind of sitting there floating, and it's held together like thanks to soft tissue.
What is it? What's the point of it?
It's amazing, actually. It's one of my favorite bones in the body. The point of the patella or your kneecap, it is protective, so there is that, just like any other bone, but its real purpose is that it gives this muscle a pivot point to exert force on. And so by having like a central point in the middle, that gives you much more leverage. And so you're able to kick way, 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 way harder than you would be without it. So like if this muscle were just to go straight down here and insert, and it didn't have this, whenever you do perform like leg extension, it wouldn't really like have that much force behind it. By just putting a little pivot point there, it's almost like creating like a much more effective seesaw, Oh,
wow.
And so it makes it like way, way more powerful. I've got a great video in our next class. Actually, you know what? I'll just pull it now because I love it so much.
Where's the ACL and like MCL?
Yeah, they're gonna be in here as well. You can't really see them here, but like, yeah, you would have like your ACL and your PCL would go like this. So they make a cross from like back to front and front to back, and they go left to right and right to left.
And those would be tendons or
Yeah, those would be ligaments.
ligament?
So it stands for anterior cruciate ligament and posterior cruciate ligament. So one's in the front, one's in the back, and they're called cruciate ligaments because they make an X, they make a cross.
Yeah.
So crucify, cross, whatever. That's the cruciate. And then you've also got, like we're looking at the side of the knee here, you'd have one right here, which would be your MCL. That's your medial collateral ligament. And so it attaches from here to here. And on the other side, you would have one that looks just like that called your LCL. That's your lateral collateral ligament. So there's actually 4 ligaments in the knee, but generally you hear about the ACL because of its positioning. It's just really easy to tear.
Yeah.
So let's see here. What the patella does for extension. Let's see if that pulls up the video that I'm looking for. Oh, come on. Where is it? Let me see here. Patellar extension. Oh, wait. No, extension. Mechanical advantage. Okay, so this creates, the reason you have your patella is because it creates what's called mechanical advantage. Mechanical advantage is basically where when you perform like, something, you want it to be as efficient and easy to move as possible. So this is a great example of that. He's got a rubber band here, and this looks just like your quadricep does. And you can see how easy it is for him to, pull on it.
Oh, yeah.
But here, he's going to remove that, and it barely moves the leg.
Oh, wow.
Eventually it would. Like if he were to really rip on it, eventually it would totally like perform extension. But you got to work so much harder. And so just by putting a little central pivot in there, it gives you
crazy.
Yeah, right? I mean, have you ever, my dad's a furniture mover. He owns a moving company up in Oregon. So I used to grow up like working with him and stuff.
Yeah.
And it's funny because I'll like move with friends, and I'm constantly like, no, put your hand down here, like lift it like that. They're like, what does it matter? I'm comfortable. And I'm like, you're not comfortable. Like, trust me, like you're working so much harder than you need to. If you go like this, you have more mechanical advantage. Yeah. And like, if I were to try to explain mechanical advantage to my dad, like he's never studied anatomy or anything like that, but he would totally get it because he can pick up like a couch by himself and he's 55 years old, like, oh, wow, yeah. And he's skinnier than me, like, and it's just my dad understands like how to leverage things and lift them properly.
You just learned it in a different way, huh?
Yeah, man. And that's what good form is too. I mean, it applies directly to us in the gym.
Yeah.
Okay, so now types of synovial joints. So this is another big part here. We're going to have 3 primary types of synovial joints. We are going to see what are called gliding joints, which is when a joint that glides across the surface of another joint. Classic example of this are the joints of the wrist and ankles are great examples, right? So when you look at like your wrist, am I going to get a picture? No, God. Wrist joint. So you're going to see a lot of what are called cuboid bones, which are bones that are named after their kind of squarish shape. And so here's like where your main forearm bone is coming together, and there's the second one there. And then you see these little like cuboid bones here, which are kind of squarish in shape, right? Okay. Here's a really great example. These are basically what are called your carpals. Then you've got your palm, and then you get your individual fingers. So these carpals, when you move your wrist around like this, they're constantly just kind of sliding like this. It's like 2 squares that can just kind of slide in a bunch of different directions. But we don't want them to like look like this, where there's no connection before, because that is a dislocated wrist. So those are gliding joints. Now we've also got hinge joints, which is where a joint that allows movement primarily in one direction, right? So it's literally like hinging. So the elbow is a great example of this, right? Your elbow is a hinge joint. Now there is another structure there that allows rotation, right? That's going to be a pivot joint. But when we describe the elbow, if we look at it, what we're seeing, right, is we're looking at this joint right here. And then there is a pivoting action that happens on that second bone nearby. So like see here, your ulna coming in and inserting onto your humerus there, that's the hinging action, right? It circles around and then it'll kind of slide back into place whenever you are extending. Now there is a second one here, like your radius, where it's interacting with your ulna, right? That is the pivot action that we're going to see in the next one. So lastly, we've got pivot joints, which are a joint that allows rotation, right? Classic example of this is like your cervical vertebrae, right? Your neck, right, I'm pivoting side to side, you know? What if I just went all the way around right there? I was like, oh, turn the video off. All right, so those are kind of three main categories there. Now we got a couple special ones here as well, which are pretty specific. You've got things like condyloid joints, right, which are allow movement in two directions. So these are like the joints between like your metacarpals, like your palm. If you look at it, your palm can do like a little bit of movement, right? Like it can perform a little bit of like flexion and extension there, kind of weakly, right? Like at the wrist. But you can also, you know, squeeze your palm like this. So there's a little rotation that happens there as well. And then like, you know, they're flexing a little bit, or they're adducting just a little bit. So those are really good examples of like condyloid joints. They're like hinge joints, but with a little bit of extra movement. So the joints between metacarpals. And then you got one saddle joint in the whole body. Well, technically you have two because you got two thumbs. But that is like a condyloid joint, but with a bit of extra movement. All right, and that is the thumb. That's the only example. Your thumb, it can do this. It can do that, but it can also do just a little bit of rotation, but it's not great at it, and that's why it always snaps when you get to that one position. It's like, and then it kind of moves really quickly. It kind of falls back into place, which is me in a saddle. And then lastly, everybody's favorite joint, the ball and socket joint. And this is the joint that allows the greatest amount of movement. It can perform all joint actions, okay? And so that, I said types of joints, right? Yeah. That is going to be the shoulder and hip joints, okay? Those are your classic ball and socket, right? Lots of movement here. Okay, so I am just gonna mention a couple more key terms here. This is gonna get pretty heavy in terms of like terminology. I would definitely spend less time memorizing joints, but this next stuff that we're mentioning is a little bit more important. However, don't be like super nervous about it if we move through it really quickly, because all of these terms are literally what we spend our entire kinesiology class going over. So like, you know, anatomy and physiology is like a bullet point of like everything. So it seems like we're moving really fast because we are, but we're going to go over this stuff in particular, like very in detail next module.
Okay.
So I always like to make sure that, you know, because people are like, whoa. So our movement.
Aren't the PowerPoints, we could always just go back and look at them, right?
Yep, absolutely. So we've got flexion, which is going to be a bending of two joints where in the sagittal plane where the angle decreases. So what flexion is when your angle decreases and it only takes place in the sagittal plane. So the example of this, that's elbow flexion. This right here, that's hip flexion, right? This is knee flexion, right? So I just basically describe whatever joint I'm talking about, like what joint am I talking, and your shoulder can do it, right? Remember, it's a ball and socket joint, so it can do everything. So this is shoulder flexion, right? Now, it seems kind of weird because you're like, wait a minute. Elbow flexion, I brought my hand up. Shoulder flexion, I also brought my hand up. Hip flexion, I brought this up, right? So a lot of times you think like up is what makes something flexion, but that's not how it works. What it is if the angle is decreasing. So I've got my arm like this, right? This is 180 degrees. Like if you were to take a protractor and you were to measure it, right? So I've got that little arm and you open it up like this.
Yeah.
Right? I'd measure it, this would be 180, right? It's flat. If I were to go like this, now the angle is 90.
Yeah.
45, 30, right?
Okay.
So that's flexion. Extension, exact opposite, right? So I'm actually just gonna be lazy here, which is how I get ahead of you guys. Which is a bending of two joints in the sagittal plane where the angle increases. And I know that like it'd be way clearer for me to say like a straightening of two joints, but I like to say bending here on purpose because it just goes to show you like how our anatomic terminology kind of becomes important. So that's flexion extension, right? If I'm going from 90 to 180, that's extension. Now in the opposite plane, not the opposite, but if in another plane, if you talk about the frontal plane, right? So all of that was moving kind of this way. But if I start going this way, right, the lateral stuff side to side, now we've got abduction and adduction. So abduction is a bending of two joints away from the midline. Okay, so we are moving further from the midline. So if I take my arm and I abduct it away from me, right, it's moving like my midline is here, it's getting further away from my midline. That's abduction. Oh, and I forgot to say, in the frontal plane, away from the midline, right? So like abduction, and then adduction is the opposite, moving towards my midline, right? Abduction, adduction, even abduction, adduction, right? So adduction is exactly the opposite. And I know they sound exactly the same, which has got to be way worse over video call. I mean, I have trouble with this. I have trouble like with this in person. Towards the midline, okay? So that's a frontal plane movement. And then we've got circumduction, which is a bending of a joint in all planes. A bending of a joint, a rotational bending.
Would that be the shoulder again?
Yep. Bending of a joint in all planes of motion. So circumduction, right? Big circle, right? Or my hips, right? Like circumduction. It's a little bit of flexion. It's a little bit of abduction. It's a little bit of extension. It's a little bit of adduction. And it's a little bit of rotation, right? Which really should have been first, actually, in the order that we're going, but whatever. And rotation here is a rotary movement of a joint taking place in the transverse plane. So remember how we move along our planes, right? If I'm being divided this way, I'm moving this way. If I'm being divided this way, I'm moving this way. Well, if I'm cut in the middle here, I would be able to rotate side to side, right? That is rotation. So these motions here, right, or this motion here, that's rotation. So my spine, it's not super great at circumduction, right? But it's performing ever so slight bits of it if you look at like the entire movement. But it doesn't really work that way because this is a bunch of different bones, right?
Yeah.
But the ball and socket joint, it's doing circumduction because it's one joint doing literally everything.
How many bones are actually in the spine?
Oh no, that's actually, that one is easy to answer and I should remember it, but I don't. Oh no, hold on, let me look at it. How many vertebrae? It depends if you're counting the sacrum as 3 bones or not. Let's see here. Yeah, you got 7 cervical, 12 thoracic, 5 lumbar, and then they count these as 1, but technically this is 3 bones that are all fused together.
Yeah.
So I guess that's 19, 24, 25, 26.
Nice.
I have not, I don't really think about it that way anymore. If you were to ask me how many cervical vertebrae you have, I would say 7, but like I haven't tried to total them up and probably since I was, you know, curious. All right. Now your forearm and your ankle, these have some special movements that I'm not going to spend too much time going over today. We will definitely go over these in our kinesiology class, but special movements of the forearm and the ankle, because your forearm and your ankle are where 2 bones actually come together and they're arranged next to each other. So, you know, earlier when I showed you the elbow, right? The elbow, like the ulna and the humerus, they're doing the flexion extension, but then your radius is right next door. And so it allows you to do the rotational movement.
Yeah.
That is the same arrangement that you have at your ankle as well. In fact, that's actually, and this is just a fun little fact that you don't need to know, but that's actually something we see in mammals. Mammals have this thing called the 1 bone, 2 bone, lots of bone structure, which is hilarious because it sounds like Dr. Seuss.
Dr. Seuss.
Yeah, like on a day that he couldn't figure out how to rhyme stuff. So you have 1 bone, 2 bones, lots of bones in your wrists, and then digits. And that's something we see in all mammals. But that 1 bone to 2 bone structure allows you to have these 2 special movements called pronation and supination. So pronation is when you are moving something and rotating it face down. So like if I'm laying on the floor, a lot of times you'll hear people refer to that as the prone position. Or if I'm laying face up, sometimes they'll refer to that as a supine position.
Supine?
Yeah, crunches are like in a supine position, and then like Supermans are in a prone position. Which is where you'll actually, one thing you're going to learn is that NASA renames everything. And so planks are called prone iso abs because you are face down.
Okay.
And then the Superman is going to be called prone cobra because you're face down.
Okay.
So pronation is where you're moving palm down, like face down, and supination is face up. One of the easy ways to remember this, if you need help, is give me soup. That's like a really good mnemonic.
Oh, yeah.
Now you've also got inversion and eversion. These are special to the ankle, which I have no way of showing. But basically when you turn the bottom of your foot, well, I guess I could just step back here. When you turn your foot like face inward and you're showing the bottom of your foot towards your midline, that is inverted. And then when you turn the bottom of your foot, which happens way, way less, but if you show the bottom of your foot towards the outside, that's everted. And then all of this is mostly upright, but then we get to the feet that jut out like this. So they have their own special versions of flexion and extension, which we're going to call dorsiflexion, which is pulling back this way, and plantar flexion, which is pointing your toe down that way.
Okay.
We'll get to those later. Trust me, you're going to be super familiar with these later on. We've also got scapular movements that they're not even mentioning here. But there's flexion and extension, right? That's classic examples. Abduction and adduction, and then like bits of circumduction. And then, oh, there's the foot. There's the eversion, inversion. All right, so that was a lot, right? That's a lot for the bones. Gets pretty heavy duty there. So bones, joints, and then technically the third part, like I said, is like bone, is like joint tissues and stuff, which is the third thing that makes it up, which is kind of built into our joints here. So let's go ahead and dive into the muscular system, shall we? Do you have any questions before we move on?
No, I think I've been asking as like we go.
Cool, no problem. All right, so actually before we start this, I gotta pull up the video. YouTube. This is definitely where the animations come in real handy. Crash course muscles.
Late night cheese craving. Same template.
If you do watch this one again, you will. Romeo and Juliet.
Oh God, that's quick.
Paris, Tristan and Romeo and Juliet, Helen in Paris, Tristan and Isolde. These famous star-crossed lovers bring to mind insatiable longing, forbidden love, and tragic separation, and poets and emo rockers love them for it. But you know where else you can find a nice hot romance? Your muscle cells. They've got their own famous coupling, a pretty pair of tiny protein strands called actin and myosin. Romeo and Juliet may have set a chain of tragic events into motion with their infatuation, but deep down in the cells of your muscles, the hot protein action between actin and myosin is actually literally causing all of your motions. All of them. And I don't just mean voluntary stuff like walking down the street or moving your mouth so you can talk or chew chips, because your muscles also support your weight and help fend off gravity. The amazing thing about your complicated, self-healing, blood-guzzling muscle tissues is that they turn chemical potential energy into mechanical energy, or movement, simply by doing two things: contracting and relaxing. And that contracting and relaxing is exactly what's fueled by the constant coupling and separation of biology's greatest lovers. Somebody get these proteins a movie contract. You will recall from our early lessons on tissues that you're kept alive and moving by three types of muscle tissue: smooth, cardiac, and skeletal. Your smooth muscle tissue is found in the walls of all your hollow visceral organs like your stomach and airways and blood vessels, where it involuntarily and very usefully pushes fluid and other material around by contracting and relaxing over and over. Your heart is so important that it gets its very own muscle tissue type, cardiac muscle, which looks striped or striated and also functions involuntarily to keep your blood pumping without you having to think about it. But when you hear the word muscle, you're probably thinking of the kind that you see on Chris Evans when he first walks out of that machine in Captain America. And those types, the ones you can see and feel and flex, are your 640 skeletal muscles. They're striated like cardiac muscle tissue, but they're also mostly voluntary, meaning you have to think about using them and activate them with your somatic nervous system. Most of them attach to your skeleton and create movement by pulling bones in different directions as they contract. Each one of your different skeletal muscles, like your biceps brachii or vastus lateralis or gluteus maximus, is technically its own organ made up mostly of muscle tissue, but also of connective tissue, blood vessels, and nerve fibers. And because your muscles are voracious energy hogs, each one is rigged up with its own personal nerve to stimulate contraction, and its own artery and vein to keep it well fed with all the blood and oxygen and nutrients it needs to operate. So to understand those operations, we first need to get a grip on the anatomy of a skeletal muscle, which involves fibers within fibers and lots of layers. Basically, a skeletal muscle is constructed like a really sturdy piece of rope. Thousands of tiny parallel threads called myofibrils squished together to form muscle fibers, which are your actual muscle cells, cells with mitochondria, multiple nuclei, and a cellular membrane called a sarcolemma. Those muscle fibers then form larger string-like bundles called fascicles, which combine to form the larger rope-like muscle organ like your biceps brachii. Overall, this bundles of bundles configuration makes muscle tissue fairly sturdy, but considering how much abuse your muscles take when you do something like pretty simple, like lift a big bag of dog food, it's no surprise you need a little help. That's why every muscle contains a few different kinds of supportive sheaths of connective tissue, but protective reinforcements to keep that bulging muscle from bursting. So that is the structure part of the story. But if you want to get into the nitty-gritty, the down and dirty of how you actually move, well, there are rules. Really just two main rules, and they have to do with proteins. And they're both true for a lot of the proteins we talk about, whether they're enzymes or ion channels or receptors or muscle proteins. And these rules are: 1, proteins like to change shape when stuff binds to them, and 2, changing shapes can allow proteins to bind or unbind with other stuff. So keep those rules in mind while we see how a muscle fiber contracts and relaxes. Now, remember those tiny myofibrils that bundle up to form your muscle fibers? They're divided lengthwise into segments called sarcomeres, which contain 2 even tinier strands of protein, 2 different kinds of myofilaments called actin and myosin. And it's their angsty story of star-crossed love that fuels every movement your body could possibly dream of. A sarcomere contains both thin filaments made up mostly of 2 myosin strands. Each sarcomere is separated by what's known as a Z line at either end, which is just a border formed by alternating thin filaments in a kind of zigzag pattern. A muscle contracting is all about sarcomeres contracting, bringing those Z lines closer together. All right, so now comes the romance. When your muscle cells are at rest, your actin and myosin strands don't touch, but they really want to. Specifically, that club-headed myosin wants to get all up close and personal with the actin. When this happens, and it will eventually, it's called the sliding filament model of muscle contraction. But in the meantime, like in any good love story, the pair have some obstacles to overcome. Namely, actin is blocked by a couple of protein bodyguards called tropomyosin and troponin, which keep getting in the way. Luckily, these guards can be bought off with a little ATP and some calcium. I prefer cash and nachos, but whatever. Remember, ATP is kind of like molecular currency. It contains chemical energy, and your muscles are all about converting chemical energy to motion, so they're always hungry for more ATP. Your muscle cells have lots of nuclei, but some of them also have a lot of mitochondria, whose sole purpose in life is to crank out ATP. And muscle cells also have their own version of an endoplasmic reticulum, the cell's transport and storage system, but in this case it's specialized, so it gets a special name, the sarcoplasmic reticulum. Its walls are loaded with calcium pumps, which use ATP to save up a bunch of calcium ions. And it's also studded with calcium channels that are linked to voltage-sensitive proteins in the membrane of the muscle cell. Say I want to move my arm. My brain sends an action potential along the motor neuron until it synapses with a muscle cell in my arm. The receptors on that muscle cell are ligand-gated sodium channels. So when the motor neuron releases our old friend acetylcholine into the synapse, the channels open up and create a rush of sodium into the cell as a graded potential, which, if it's strong enough, causes nearby voltage-gated sodium channels to open. Now, I want to take a second and point out here that we're still talking about an action potential, but not in a neuron. This is happening in a muscle cell, people. So that action potential zips along a muscle cell's membrane, the sarcolemma, which has lots of tubes that run deep inside the cell called T-tubules. When the action potential travels down one of those tubes, it eventually triggers the voltage-sensitive proteins that are linked to those calcium channels in the cell's sarcoplasmic reticulum. When those channels are thrown open, the calcium stored inside rushes into the rest of the cell, and finally myosin is like, yes, here we go. At this point, the myosin is totally stoked, because the bodyguards that have been frustrating it are in for a big, irresistible distraction. That's because the protein troponin just loves to bind with calcium. And remember, when stuff binds to proteins, the proteins change shape. So the calcium latches onto the troponin and causes it to pull the other bodyguard protein, the tropomyosin, away from the sites on the actin strands that the myosin really wants to get its paws on. And suddenly it's all, okay. But the only myosin heads that can bind to those newly exposed sites are the ones that are ready for action. That is, the ones that have already grabbed a molecule of ATP that's been floating around and broken it down into ADP and the leftover phosphate. When a myosin head does that, it moves into an extended position, kind of like a stretched spring, still holding on to the ADP and the phosphate, and still storing the energy that was released when they were broken apart. So after all that, with the myosin primed for action and the bodyguards out of the way, the myosin finally binds to actin, and it is beautiful. When they bind, the myosin releases all that stored energy, and in the excitement of it all, the myosin changes shape. It pulls on its precious actin strand, kind of like pulling a rope hand over fist. In the process, it shrinks the whole sarcomere and contracts the muscle. That's the sliding part of the sliding filament model. Now, with its energy spent, that little head has no use for the ADP and the phosphate, so they unbind with it because, remember rule number 2, changing shape encourages proteins to bind or unbind with stuff. That unbinding causes a small change in its shape, which lets a fresh ATP bind there in its place. That binding causes another shape change, but this time it causes the myosin to release from the actin in a tear-jerking scene like some microscopic recreation of the finale from Titanic. But fear not, this epic is not quite over, because this is when the myosin breaks down its new molecule of ATP into ADP and a phosphate, which moves it into the armed position yet again, getting it ready for its next rendezvous. And meanwhile, those calcium pumps are working hard to restock the calcium in the sarcoplasmic reticulum, so they start grabbing the calcium that's floating around, causing calcium to unbind from the troponin. When it unbinds, the resulting shape change puts the tropomyosin bodyguards back into place. It's a circle, or potentially a big Hollywood franchise with lots and lots of sequels. It keeps repeating itself many, many times every moment while I sit here and talk, and while you sit there and eat and text and take notes, the whole drama replaying itself over and over. Kind of like you'll have to play this video over and over again to get all the little steps of the sliding filament model straightened out. But hey, some stories get better the more you hear them. If you do do watch this one again, you will relearn that your smooth cardiac and skeletal muscles create movement by contracting and releasing in a process called the sliding filament model. You'd also relearn that your skeletal muscles are constructed like a rope made of bundles of protein fibers, and that the smallest strands are your actin and myosin myofilaments. It's their use of calcium and ATP that causes the binding and unbinding that makes sarcomeres contract and relax. Special thanks to our headmaster of learning, Thomas Frank, for his support of Crash Course and free education. And thank you to all of our Patreon patrons who help make Crash Course possible through their monthly contributions. If you like Crash Course and want to help us keep making great new videos like this one, you can check out patreon.com/crashcourse. Crash Course is filmed in the Dr. Cheryl C. Kinney Crash Course studio. This episode was written by Kathleen Yell, edited by Blake DiPestino, and our consultant is Dr. Brandon Jackson. Our director is Nicholas Jenkins. The editor and script supervisor is Nicole Sweeney. Our sound designer is Michael Aranda, and the graphics team is Thought Cafe.
All right, we got you back. Let's just let that
Okay,
out.
there we go.
Hey. Welcome back. What's that?
I don't know what happened. Everything just shut off.
Oh, man. Yeah, quarantine life, right?
Man. What was the video called so I could watch it on YouTube later?
Yeah. So it's Crash Course Muscles Part 1. There is a Part 2 that's really cool as well.
Okay.
But Part 1 is the stuff that has some animations that just kind of explain this, that show you this stuff pretty easily. All right, so let's, again, this is another one where like we're gonna kind of just start off with like the muscular system, right? And we'll kind of define that as it is. So your muscular system, just like your skeletal system, right? Instead of being a system of bones, joints, and connective tissues, this is going to be a system of muscles and tendons and connective tissue that is responsible for producing movement, producing movement throughout the body, right? So your muscular system's job is to manipulate your skeletal system, okay? So each individual muscle is going to be made up of individual muscle cells. Now, we do have 3 types of muscle. We're going to spend most of our time talking about one of those types. But our 3 types of muscle that we've got are going to be smooth muscle, which is, actually, am I going to get? No, we're not. So smooth muscle is going to be like the walls of organs, right? Like your digestive system, right? It needs to be able to contract to kind of move food around, but it's not really like, it's not lifting any weights. Although it feels that way if you eat something you're not supposed to. You're just like, oh. So those are like the things like the walls of your organs. And then we have like cardiac muscle, right?
Like the heart.
Yep, the muscle of the heart. And then finally, we have skeletal muscle, which is muscle responsible for manipulating the skeleton. So that's your skeletal muscle, right? This is primarily what we're spending our time talking about. You can kind of see the reason we name them different things. They look slightly different, right? Like smooth muscle's entirely involuntary. This is going to be, you don't really have any control over this. When we get to the nervous system tomorrow, we're going to be talking about like the differences between like voluntary actions and involuntary actions. You have 2 main divisions of your nervous system. Some of it you have control over, some of it you don't. Your cardiac muscle is also entirely involuntary. Like I know that like all of us can like think anxious thoughts. Like if it's like, oh man, I remember that time that like, I was going to ask that person out and, they rejected me or something. And you're like, or that time I like waved to somebody and they were like, hey, but they were waving to the person behind you. And you're like, we can think thoughts like that, or we can control our breathing. And like, that'll totally slow your heart rate down. But that doesn't mean you actually have control over it. Like, I can't tell my heart, it's like, okay, heart, beat 6 times.
Yeah. No.
Like, I can't. Skeletal muscle, it's voluntary, but it can be involuntary. We've all definitely had that moment where we, twitch or something. But for the most part, our skeletal.
Why does that happen? Like a random twitch?
It kind of depends. If it happens like as you're falling asleep, that is actually because your brain works with your endocrine system, which is also a control system, under the control of your nervous system. But it's like your nervous system kind of tells your endocrine system to do this, and it's all involuntary. So your endocrine system is in charge of making hormones that like paralyze you while you're asleep. But then your brain is basically like, the manager of everything. And so it's like going by and like, it's got its little manager clipboard, and it's like, have we shut down the legs? Have we shut down this? And it starts doing a little check mark. And if that paralyzing hormone didn't quite act as strong as it needed to, sometimes you'll feel those little twitches, and they'll come out of nowhere. And it kind of wakes you back up. Or if you get itchy.
So it's basically like your body's saying, oh, we need to shut that down.
Yeah, it's like it's doing like a little rundown, like that's actually what when you sit on your foot and your foot falls asleep, and then it starts tingling. Like a lot of people think that that's because you've cut off blood to your foot, but luckily that's not true, because if you cut off blood to your foot would die, done. But what you are doing is you're pinching off the nerve. So now the foot is having trouble communicating with the brain. So because the brain is like, hey, foot, are you still down there? It starts sending these really big signals. And you've been interrupting that signal, but then all of a sudden you shift positions, and now all the signals are getting through, and you're like, ah! And your foot's, that's your foot kind of waking. That's the feeling of it being asleep.
Wow. I always thought it was the blood thing. So
everybody does, yeah, because that's what everybody says, Luckily, that's not. If that were true, you'd lose your leg.
Well, thank God that's not it.
Right. All right. So let's look inside of a skeletal muscle, right? So a skeletal muscle is three primary functions. It's in charge of moving your skeleton around, maintaining posture so that it keeps your bones in the positions they're supposed to be in, although Lord knows we're all bad at that. And then it's also in charge of a little bit of heat generation. Like when you get cold, you'll naturally start moving around a little bit, which promotes blood flow, ATP production, and energy production, and things that kind of heat us up. Now, when we look at a muscle, right? If we're looking at a muscle structure, so a muscle is like, each of your muscles is considered its own individual organ. If we think of the fact that, like, if we go back to like our levels of organization, right? You've got chemicals make up cells, cells make up tissues, tissues make up organs. So a whole bunch of muscle cells coming together makes up an individual muscle. That's technically its own little organ. I know a lot of times we think of an organ, we think of like, the stomach, but like that's just a series of tissues. So every single one of your muscles, of which you have, depending on who you ask, sometimes up to 800, each of those individual muscles is considered its own little organ. And that is basically a bundle of what we call muscle fibers, okay? So when we refer to a muscle cell, we don't usually say muscle cell, we're gonna say muscle fiber. Muscle structure, yeah, we'll just leave that as our section. So they are bound up, and actually I'm gonna put that up here really quick. So a muscle fiber is an individual muscle cell, okay? And then you've got what's called a fascicle. And fascicles are bundles of muscle fibers that make up the whole of the muscle, right? So actually, you know what? We'll do this. I'm gonna go in this order. So then you have a muscle is an individual organ that is a bundle of fascicles. So here's what's kind of cool about muscles, right? And I'm going to see, there's a great picture of this here. Muscles are bundles of bundles of bundles of bundles of bundles. So you've got an individual muscle cell, and then all these muscle cells come together to make up a fascicle. And then all of those other fascicles, which have the same arrangement, all come together to make up a muscle belly. And then that muscle will finally insert. So like bundle, 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 bundle. It's a big rubber band ball, you know?
I really know.
And then one other thing that we are going to see is also like a tendon. And a tendon is going to attach muscles to bones. Now, within that muscle, you're going to see three primary layers here, right? Three primary layers. And this is mentioned plenty of times, but honestly, it doesn't come up that often. You're going to have your endomysium, which is the innermost layer. It makes up the wall of each individual muscle fiber. So like when we look at like a muscle fiber, right, it's like any other cell. It has to have like a membrane around the outside to keep everything in and keep some things out. That's going to be referred to as your endomysium. Endo means most inner, right? Then you're also going to have your paramysium, right? And that is going to be the uppermost layer of a bundle of fascicles, right? And so your paramysium means it's around the perimeter, right? That's where we get that word there. And then, actually, I shouldn't even say, actually, I should say the outer, because that's really what it means. Outermost layer. And then the epimysium is the uppermost layer of a bundle of, oh, you know what? I'm so sorry. I shouldn't have said paramysium is a bundle of fascicles. I should have said a fascicle. The outermost layer of a fascicle. Sorry. So one fascicle, which is a bundle of muscle fibers, that sheet that holds the fascicle together, that's your paramysium. Your epimysium is what holds all the fascicles together. A bundle of fascicles. Does that make sense?
Yeah.
So shell, shell, shell. And then you're also going to have like one thing they're not mentioning here is like sometimes you'll have another outer layer of like fascia. And fascia is just there to kind of keep your muscle in its overall arrangement and sometimes hold muscles together. Like there's a lot of fascia in your quadriceps, for instance, that kind of make sure that like the four muscles that make up your quad don't like randomly like fold over each other or anything.
When we work out, what part of the muscle is what breaks down and rebuilds to get bigger?
So that's the thing. Every single individual muscle fiber.
Oh, wow.
Yeah, that's what's so crazy, right? And that's what we're about to get into. We are about to zoom in like crazy. And there's going to be a lot of terminology in this section. It can sometimes be a little intimidating, but like that's what we kind of need to understand. The big thing they do want you to know when it comes to like the main anatomy and physiology of muscles is they want you to understand this concept called the sliding filament theory. And the sliding filament theory basically describes how each individual muscle cell shortens like this. They have these little proteins arranged in them and they slide across each other. And that happens in this muscle cell and this one, 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 and then all those are wrapped together, and then all of that's happening to all the other, and it's all happening at the same time. So that's actually how you have strong contractions and weak contractions. Like a strong contraction and a weak contraction, what's kind of crazy, they both get the same electric signal from the brain. The signal is identical in a 500-pound deadlift as it is to pick up a 3-ounce kitten, you know?
Wow.
Same electric signal. But what determines like picking up that super heavy barbell and not flinging that kitten in, you know, into the air is that you have these things called motor units. And so like you might have one neuron that splits off and it innervates that fiber, and that fiber. That's only 3 little fibers. That's not a very powerful contraction. But if it innervates that one, you know, just thousands of them, that's a big, strong contraction. So the more muscle cells you recruit, the stronger the contraction.
Okay.
And how do you determine how many cells you recruit? That's under the control of your nervous system, which is what we'll look at tomorrow.
Right.
So
what causes cramps in the muscle?
yeah, totally. It's so funny, man. You just At this point, every time cramps come up. That's so funny.
Wow.
I guarantee, like, I'm going to say this for the people who are watching the recording. I know your brains were thinking the same thing. I don't know what it is. It always triggers right there. So cramping is, there's a couple different things. It can happen when your muscle contracts, but then it can't like create an anti-signal to uncontract it. So like, because there's no fluid, like if you're dehydrated, you can cramp up.
Yeah.
But similarly, if you don't have like sodium or potassium to generate electricity, so if you're low on sodium or if you're low on potassium, that's why everybody says eat a banana when you're cramping, because bananas are high in potassium. But sometimes they'll say, oh, you need some electrolytes, which is stuff that's high in sodium. Sodium and potassium are both electrolytes.
Yeah.
So if you're like low on that stuff, your nervous system can't generate electricity, and so it can't stimulate the muscles the way it's supposed to. So instead, what happens is you get like a bad contraction that you're not really trying to control, and so that is a spasm.
Yeah, last night I got woken up by like the worst calf like cramp. I was like, what the heck?
In the calves?
Yes.
Oh, that sucks.
Yeah.
Use that foam roller. Yeah. That'll help a lot, actually. Break up some of that. That's also sometimes like there's like lactic acid can cause the buildup of like hydrogen ions, and all that hydrogen, like that positive hydrogen stuff, keeps your contractions from happening. That's actually why you can't continue lifting. Like when you get weaker and weaker and weaker, like as you go higher in the sets, you're not actually getting weaker, but you are building up more and more lactic acid and hydrogen. And so it's like, eventually you have to stop. So this is where we come to what is called a motor unit. Okay. So motor unit is a single motor neuron from the nervous system and all of the individual muscle fibers that it stimulates or innervates, right? So you get small motor units for things like your eyes. You know, there's a couple hundred motor units that control your eyes moving around, and there's several thousand motor units that control, you know, hip extension and things like that.
Yeah.
Now, we have to have a point at which your nervous system pokes your muscular system. So you're going to see a structure that kind of looks like this, and there's a little gap between the two. That's what's called your neuromuscular junction. So at the motor unit, you have the neuromuscular junction, or NMJ, and this is the point at which a nerve fiber contacts a muscle fiber, right? So this is the point at which the nervous system can interact with the muscular system. So this is what we refer to as like a synapse. A synapse is basically whenever a nerve touches anything, that's a synapse. Like a nerve touching a nerve touching a muscle, nerve touching a gland, the area where they connect, that neuromuscular junction, that's what we call a synapse. So what you're going to see at your neuromuscular junction is you're going to see the motor neuron, right? There it is, right? There's the neuron as it comes down, and there's that little gap I mentioned. And so that's the neuron. Then you're also going to see a neurotransmitter. And a neurotransmitter is basically a chemical that your brain can create, or that your nervous system that can create, that will bind with the muscle. So here, you'll see that little neurotransmitter, right, which are these little green things here. That's what's called acetylcholine. And acetylcholine.
Acetyl what?
Acetylcholine. It's right here, ACH.
Okay.
And so acetylcholine is the neurotransmitter. What will happen is like when the electricity runs down this, that triggers the release of acetylcholine. And so it moves across the little gap, and then it hits this little sensor receptor here, which the sensor receptor is arguably, you know, still part of your nervous system, but it's attached to your muscle.
Okay.
So this little receptor right here, as soon as acetylcholine binds to it, that tells the muscle to generate its own electric signal. And so it will flush sodium and potassium throughout it. So electricity travels down the neuron. It goes from neuron to neuron to neuron to neuron to neuron until eventually it gets to the very end. And then acetylcholine moves across, and then it hits the muscular system. And then the muscular system generates its electric signal. And that electric signal is going to cause the flushing of some materials that are going to create contraction. Okay. So that's what we call and that is all, that little place right there is called the motor end plate. And that motor end plate is what houses those receptors. So you're seeing that's the end plate, right? The dark blue bit. And then that's the receptor right there. So these are the things that are happening. This is going to sound like I'm going through a lot. I'm going to go through this a few times. So the neuromuscular junction will stimulate a muscle fiber by creating an action potential, generating electricity, right? That action potential will stimulate muscular contraction. So electricity travels down the neuron releases acetylcholine from the neuron into, and that area is sometimes also called the synaptic cleft. Thanks a lot, PowerPoint. It's like throw another term out there randomly. The space, it's a synaptic cleft. And so it will diffuse across that cleft towards that motor end plate we mentioned with the receptor. That receptor will bind to it, and that will stimulate the muscle's action potential. So now the muscle will run electricity around its body. And then you can see, this is kind of cool. You can actually see what it looks like, right? There's the neuron, there's one fiber, there's a different fiber, there's a different fiber, there's a different fiber.
Yeah.
Kind of cool, right?
Yeah. What is that, like that's not an X-ray, huh? It's like a CAT scan or something?
That's just an electron microscope.
Oh.
Yeah. That's just using a super advanced like microscope.
Yeah.
Which is awesome. So here's what's really cool. Now, looking at the end of this, let's look at a muscular contraction. So muscle contractions, okay? Muscle contractions are going to take place in this area called the sarcomere. Now, the sarcomere is not technically like a thing that you can hold. Like all these things we've talked about, right? Like a layer is almost like a physical thing you can touch. A sarcomere is a term that is kind of like an area. It's kind of like, downtown. Like, there's a difference. It's all Los Angeles, but like downtown's a section, right? That's kind of like what a sarcomere is. So a sarcomere is where contractions take place in a muscle cell. So this is the functional unit of the muscular system. It is where muscle contractions take. It is where contractions take place in a muscle fiber. Okay, so that's the sarcomere. So your sarcomere, you remember how we mentioned how all cells have like special structures related to them?
Yes.
Muscle cells have these little things called myofilaments. So myofilaments are special proteins responsible for creating contractions within muscle cells, okay, or muscle fibers. Those two filaments are going to be actin and myosin. So you've got actin, which is the thin filament. It has special binding sites that allow myosin to bind to it, okay? So actin is basically this thin little strand full of all these little like special binding sites. Myosin is the thick filament. It has special heads that like to bind to actin, okay? And then you have special proteins called troponin and tropomyosin, which are regulatory proteins that keep myosin from binding to actin when the muscle is relaxed. So troponin and tropomyosin are there to keep this action from happening. But actin and myosin really are attracted to each other and they really want to get together. So here's your sarcomere. That's
Romeo and Juliet.
What's that? That's Romeo and Juliet, right? And then here's their families. So you can kind of see how they're making kind of a zigzag.
Yeah.
All right. Well, let's zoom in on that like crazy. So the sarcomere is taking place because of what is called the sliding filament action, or the sliding filament theory, or the sliding filament mechanism, whatever you want to call it. But the sliding filament model describes how myosin binds to actin to create muscular contractions, right? So what happens here is, using stored energy, myosin will bind to actin and pull towards its center. Meanwhile, this is happening in other sarcomeres simultaneously. Causing the overall muscle cell to shorten. Okay, so what's happening is, like, all of these sarcomeres are binding together simultaneously. And so you can see here, right, this is a resting muscle. This whole area is the sarcomere, right? And so these are the myosin heads right here, and these are the actin sites. So this little thin strand is kind of held together. This right here is called a Z line, and this is called a Z line. And it's called that because it kind of, like, what you can't see is there's another sarcomere right over here, and that actin strand is attached in the middle between each of these. So it makes a zigzag.
Okay.
And they're arranged, I guess, rather than being arranged like this, they're arranged, you know, offset like that. And that creates like the Z. So what's happening is, like, these myosin heads, they're going to reach up and pull. Meanwhile, that's happening on the other side. So they're both pulling this way. And that is going to take your muscle cell from being this long, and it's going to make it this long. Remember earlier where I was talking about bad posture and how that's created by, like, muscles that can't relax? That's why we need to foam roll, right?
Yeah.
Well, what's happening is, literally, your nervous system can't shut down this signal. And so your muscle's just staying in this kind of shortened state, right? If I got rounded shoulders, right? I'm sitting like this. That's because my pec is contracting 24 hours a day, 365 days a year. And so I'm sitting like this. But if I do, like, stretches like that, I can get my shoulders back to a neutral position. Now, meanwhile, while this is happening, this is squeezing too hard. These muscles in my upper back, they're pulled too far apart. And these actin and these myosin proteins, they can't grip each other effectively. They're missing each other. So I've got an overactive muscle here, actively pulling me this way, and I've got underactive muscles here that are being pulled in the opposite direction. So as a trainer, my job is to stretch the overactive stuff out and get it to relax, and then to strengthen the underactive stuff to get it to pull me back to neutral. And that's how we fix posture as trainers. Which is why this stuff's important. Like, it's like, man, like, this is so much like inner anatomy. How is this at all relevant to me? See, right? It all actually does connect.
Everything.
By the way, watch that second episode of Crash Course on muscles. It'll talk about one of my favorite things when it talks about the sliding filament model. What's crazy about the sliding filament model is that it was discovered. This is my favorite little story, so I apologize for taking a little break here, but I did it. This is like one of my favorite stories. So sliding filament model was discovered by so-and-so. Wiki. I've looked this story up before. Yeah, it was discovered by, in what year? 1939. Is that right? That's not right. 1952. It was discovered in 1952 and like introduced into a paper in 1954 by two guys, Andrew Huxley and this other guy named Rolf Niedergerdt. Andrew Huxley, by the way, was he was part of a very rich family of other Huxleys. If you've ever heard of the book like Brave New World, that was written by Aldous Huxley, right? And so it's kind of like the very famous family. But these two guys were in Cambridge and they were looking at muscle cells and then they saw this happening. And so they came up with a theory and they named it the sliding filament theory. And so then they needed to publish their findings. So they published it in a medical journal. Now, at the exact same time, another scientist group at the Massachusetts MIT in the U.S. named Hugh Huxley and Gene Hansen also discovered the same thing. And
Is it a different family or the same family, Huxley?
so that's my favorite part of this. They are not related at all.
Oh, wow.
And so they both published their findings in the same medical journal. Because that's how it works, right? You just send it's like a publication. They both, and like the publication doesn't check the article, you know, they just put them, they're both in the same medical journal describing the same thing, the same year.
That's crazy.
Issue, and two of the scientists have the same last name. That's a glitch in the matrix, right? That's two black cats.
That's crazy.
Yeah, I love that fact. That's my favorite little weird story. I always thought that would make like a really good movie, but probably not. I feel like the audience would get really bored. But anyway, when it binds, it creates this sliding action, right? These proteins slide towards the middle. These proteins slide towards the middle. So in an overactive muscle, they're already slid together, right? This is a muscle that isn't relaxing. And in an underactive muscle, they're too far pulled apart, which is why we want to get back to neutral posture.
Yeah.
So now there is going to be like I'm going to give you a quick rundown of this, just because we always do the rundown, but honestly, don't worry about knowing this until way later classes. This is very much something we will go over a lot, but we will cover it in detail in our physiology class. So what's interesting about like what creates these contractions, remember troponin and tropomyosin, they're the chaperones that keep the binding from happening. So yeah. If we want binding to happen, we need to get those guys out of the way. How do we get those out of the way? Well, troponin is actually what's mostly responsible for that. Tropomyosin is actually kind of this big long string that just sits on the actin, but it has these little binding sites called troponin. And troponin is super, super, super attracted to calcium, actually.
Oh, wow.
And this is what also might lead to cramping here in just a second. So calcium is actually what draws troponin away. So when I mentioned earlier, like your muscle cell sends an action potential, it generates electricity along the muscle, that triggers the release of calcium into the sarcomere. And when that calcium moves in, troponin can't stand it. It's like, oh my God, I gotta go get with that calcium. So it moves away and it drags the tropomyosin strand with it because it's attached. Yeah. That means now actin's binding sites are open. And it's like, oh, it's on, right? And it gets up in its business and pulls it. And then once that signal is done being created, we flush all that calcium out and that causes the muscle to relax. So what causes cramping? Sometimes it can be a lack of calcium, actually. Yeah, you wouldn't think calcium is important for muscular contractions, but it is the most important for muscular contractions.
Wow.
So you can kind of see that happening right here, right? There's the troponin, here's the tropomyosin. Tropomyosin's the rope, troponin's the protein. If you put calcium in there, it draws it up. Now the binding site is exposed, and the myosin head grabs it and pulls it.
Okay.
And so here's a big summary of everything that's happening. I'm just going to say it all one more time. Acetylcholine is released from the neuron. That acetylcholine binds to the motor end plate. That triggers an action potential in the muscle. The action potential runs across what is called the sarcoplasmic reticulum. It's basically a network of tubes that allow calcium to travel around. Calcium is then released into the liquid portion of the muscle cell. That causes troponin and tropomyosin to move away. Myosin binds to actin and pulls using its stored energy. Then finally, a new ATP molecule moves back into place. That causes the protein to change shape and let go, which flushes all the calcium back, and your muscle relaxes. Whew! Yep, exactly. Honestly, you don't need to know every single one of those steps, but what you do want to definitely know is that like the sliding filament model is responsible for contractions, and it's able to do that with the assistance of these 4 proteins. So everything that's in the notes.
Right.
Now, all that other stuff that we left out of the notes, it helps you understand the notes, but like we don't need to put it in here. So where do you get all the energy to do this? Well, all that requires ATP. How do we produce ATP? And by the way, we haven't talked too much about ATP yet, but we'll get to it later. ATP is our energy, right? That's how we break down and do work. So how do you get all that energy? You get it from carbohydrates like glucose, and you get it from oxygen, and sometimes you'll get it from fats. How do you carry that stuff around? Like, how do you make sure that your muscle has plenty of ATP fuel? Well, it's got to have things like myoglobin, which is a protein that holds onto oxygen molecules found in your muscles, right? Myo for oxygen, myo for muscle, globin for oxygen, and glycogen, which is glucose, right? That's stored up glucose. So you've got plenty of oxygen, you've got plenty of glycogen stored in your muscles, which means when you need to do work, you can. So we're happy for that. So that's all going to happen thanks to our energy sources, such as breaking down. Sometimes you can do it through creatine phosphate as well. We'll talk more about that in later classes. Sometimes it can do it through anaerobic glycolysis, where it produces it in the fluid portion. It can make ATP there. Or it can do it in the mitochondria, where it's going to use oxygen in order to do that. So whenever you exercise, that is great because it creates all these it creates all this cellular work. All this stuff starts happening, and that actually damages your muscles. So when that happens, it increases your muscle size, which we call hypertrophy, right? I damage my muscles. My body goes, "What did you do to my pecs?" You know, like you broke everything, you know? And then it goes, all right, well, if you're going to keep breaking crap, I'm going to make it bigger and more resistant to damage. Okay. And so then it builds up new muscle cells and makes those muscle cells larger by making more actin and myosin proteins.
What causes that? You know, when you plateau sometimes when you're working out so much, what causes
you get stuck. There's a lot of things that cause plateaus. We actually have a whole day on plateaus in the mod just before you started. We actually just talked about this about a week ago. Okay. But basically it comes from your body adapting to a specific amount of stress. Remember, like exercise is stress that causes an immune reaction, right? Like, you know, they were talking about like the coronavirus. When people got like sick from it, those people were, they thought immune to catching it a second time afterwards because their immune system was super like, what the hell was all right, nothing's getting in anymore. You know, like, and theoretically that was true, but the virus is kind of tricky. Yeah. Well, that's what happens anytime you catch a cold. You're pretty tough afterwards. The same thing is true of your muscles. If you damage your muscles, if you damage your bones, if you damage your nervous system, all those things build up a little stronger and they become more resistant to damage thanks to your immune system. But the thing is, if your body's like, I've experienced that stimulus before, we survived in the past, we'll be fine this time, it has no reason to get bigger. Okay. So plateaus are caused by like the same type of stimulation too often. Okay. So you can keep that from happening by like, you know, changing it. Yeah. Mm-hmm. So exercising, our favorite thing, it increases your hypertrophy. It increases your muscle tissue in general. It gets better at contracting because then it gets to learn how to work with the nervous system more efficiently. You're going to see more vasodilation, which means your blood vessels actually get better at sending blood to the muscles, because that's how you get oxygen. It strengthens your heart. It helps you control your weight, and all that damage also creates stronger bones. So holy crap, we love working out. Now, working out is a series of different types of contractions. So this is a contraction in general, but there are 3 main types of contractions that are occurring that we're going to use and talk about. So our types of muscle contractions, we have got 3. We've got eccentric contractions, which are contractions that occur when a muscle is lengthening. Okay, so if I've got my bicep like this, right, and then I let it stretch out like that, that's a lengthening action. That's an eccentric contraction, right? The muscle is generating less force than a resistance. So if I've got a 10-pound weight in my hand, but I generate 9 pounds of force, it's going to lengthen my muscle. That's eccentric contractions. It is force reduction. Okay, but then we also have concentric contractions. Concentric contractions are contractions that occur when a muscle is shortening, right? So the muscle is generating greater force than a resistance. It's force production, right? And so when we think about that, right, if I've got my bicep here and I contract it, right, it bunches up. That's force production. I've got a 10-pound dumbbell, I generate 11 pounds of force, right? Okay. And then we've got isometric contractions, which are contractions that occur when a muscle length remains constant, okay? The muscle is generating equal force to a resistance. That's force stabilization. So basically, if I've got a 5-pound dumbbell and I generate 5 pounds of force, I can hold it in this position and just kind of stick there. If I push as hard as I can against a wall, I may be trying to produce more force, but I'm not. I'm generating isometric. I'm equaling the force that the wall is pushing back. Isometric contractions are exactly an example, like a wall sit or a plank.
Oh, yeah.
So if I had like, if I was doing like bicep curls, right, that would be concentric. This pausing would be eccentric. I'm sorry, this pausing would be isometric, and the lengthening would be eccentric. So eccentric, isometric, concentric.
Okay.
Now, last little bit we got to do here. We're almost going to leave this alone. We already mentioned tendons. Your tendons are going to attach your muscles to your bones, right? They're going to do that in 2 places. Your origin, which is closer, is the more proximal part, and the insertion, which is the more distal part. So when you look at like your bicep, right, it's got a tendon here and a tendon here, right? Those both insert onto the scapula there, and then they run down and they insert onto your forearm here, right? This is why it's called your biceps, by the way, because there's 2 separate sections of fibers here. One that attaches underneath, like right here, and one that attaches a little bit more like right here. And that's why if you ever see somebody doing like, this is why I am personally not, I mean, I'm not here to say it's bad, but I'm not like a big fan of mixed grip deadlift. You know, you see guys do that 1 under and 1 over thing. The reason I don't like that is, by the way, it works. It makes your grip so much easier. But the problem with it is that it overstretches this bicep tendon with your face up, your supinated palm. So you'll see people like deadlifting crazy amounts of weight because their glutes are really strong, and then this poor little bicep tendon has to keep up. And you'll see these like bicep tendon tears where all of a sudden you'll just see like, and then like they'll drop the barbell, and it's because they've like detached it from one of these. Horrifying. Or sometimes you'll see it in the wrist. But your origin is more proximal and your insertion is more distal. So whichever one is closer to the center. We're not really going to worry too much about that. The last thing I do want to worry about, though, is how we label muscles. So remember earlier I mentioned like going this way, right? Yeah. The muscles that are responsible for that are my pecs, right? These are what we call an agonist. They're the main muscle that does that. My antagonist does the opposite. But that's only if I'm describing this motion. What if I were describing this motion? Well, then the muscles in my back are the agonist, and the muscles in the front are antagonists, right? So for flexion, my bicep is the agonist, and my tricep is the antagonist. During extension, my bicep is the antagonist, and my tricep is the agonist. So that your muscles, here's what's kind of fun. Muscles as movers, okay? So muscles will move, muscles control our posture, and are arranged in such a way that they can only pull. This sounds kind of weird, but muscles can only pull. And I know that's kind of surprising because we have an exercise called the push-up. But muscles can't push. When you are doing a push-up, your pecs are pulling this way.
Okay.
So how do we get back to neutral? We have to have an opposite muscle that will pull the other way. So, which is, that arrangement is how this works. So agonists are prime movers responsible for a movement, okay? So an example, right? The pectoralis major is the agonist during a push-up, okay? That's this muscle right here.
Yeah.
An agonist is like I said, it's the prime mover. Honestly, the easiest way to think about this, it's Batman, right? Batman's the main character. He's supposed to do all the work, right? Now, you also have antagonists. You know what? I should probably just put that in parentheses. Because you ain't gonna find that in a book. Your antagonists are muscles that move opposite prime movers for a particular movement. Okay, so our example: the posterior deltoid is an antagonist during a push-up. Okay, so back of your shoulders, right? When you're doing a push-up, they're lengthening, right? Like as I push away, that lengthens out my posterior deltoid. Now you do also have synergists. Oh, and that's the Joker.
When you're doing a push-up, your shoulders is that pulling as well?
No, they're lengthening. They're being pulled. The front of your shoulder is doing a little bit of pulling, but the back of your shoulder is lengthening. Like your upper back, right?
Yeah.
Let's look at a lat pull down, right? Let's say I was doing a pull up, right? When I pulled down like this, my agonist is my lat.
Yeah.
My antagonist is the top of my shoulder, my anterior deltoid. Or let's look at, like I said, like the bicep, right?
Yeah.
Agonist, antagonist. But every muscle in your body could be an agonist or it could be an antagonist. It just depends on what movement you're talking about.
Okay.
So there's no muscle that is always an agonist.
Okay.
It's an agonist during
a
this.
certain movement. Yeah.
Yeah. So like from the Joker's perspective, he's the good guy, right? Like, like it's like he's the agonist trying to rob a bank and Batman's the antagonist who's trying to stop him.
Yeah.
Meanwhile, from Batman's perspective, he's the agonist trying to save Gotham, and the Joker is the antagonist trying to ruin it. I know this analogy is weird, but trust me, it comes around even clearer in just a second. So we also have muscles that help your prime movers, and these are going to be your synergist muscles. So synergist are muscles that assist prime movers during particular movements. So like, let's look at the pull-up or the push-up again, right? My tricep is there to help. That's a synergist, right? My deltoid is there to help as well. That's a synergist during the push-up. It's there to help Batman, right?
Yeah.
There it is. You nailed it. So the example here, right, is the anterior deltoid assists the pectoralis major during a push-up, right? Robin. Then we do have stabilizers. Stabilizers are muscles that stabilize the body during functional movement patterns, right? So the examples here is like, it may not have anything to do with your pecs, but we really don't want our spine moving around too much while we're doing this. So like the rotator cuff is keeping your shoulder in the right spot, and the core musculature is protecting the rest of the body and stabilizing during the push-up. So you get your rotator cuff in there, creating stability. You get your core and your low back, which are all, all of that's like tightening up while you're doing that push-up movement to make sure that like nothing else moves out of place in a way that it really shouldn't. Every day, telemarketers. So it's there providing like general support. This is like Alfred. Right? Alfred's there to provide like emotional support once Batman and Robin get back. He's got tea and crumpets. So there are a few other things that we'll talk about, but again, these are more kinesiology related. So, like I mentioned, your bones act as like a lever. Well, your joints are going to act as like a pivot point. That's called a fulcrum. And the force that moves that pivot, that lever through its range of motion is the muscle. And so we have different ways of classifying those in what we call lever systems. Third class is like the most common. Basically, that's where something like pulls up on something, kind of like a wheelbarrow. But you got first class as well and second class levers. Don't worry about them. We'll come back to those later. But yeah, here's your example. Like a first class lever is like your neck, right? It's like a seesaw.
Yeah.
And then you got a second class lever. Actually, that's the one that's like a wheelbarrow. And then a third class lever is kind of like, I guess like a pair of tongs.
Okay.
And yeah, that is actually it. Here's all your muscles. There's a bunch of like junk slides at the end here that are kind of going to go over like muscles that actually move your body around. Don't worry about memorizing these just yet, but it's just going to go through this big long list of like your trapezius muscles are up here and in your upper back. Your lat is down here. This is not the class for this. We have a kinesiology class where we are going to go over these things and actually teach you like what the rectus abdominis is, what it does, Actually, you know what? I'll talk about this one just really quickly. Your six-pack muscles, they are an outer shelf, and there's actually an inner shelf, which you can see they cut away and show you the inner shelf here.
Yeah.
The inner shelf stabilizes everything. That's Alfred. But the rectus abdominis, which is your six-pack, it does your crunch. That's Batman. And then you've got low back muscles, which would pull you back this way. That would be the Joker.
Okay.
And then your obliques, they actually do a little bit of flexion as well. So they're like Robin.
Yeah.
But anyway, it's going to give you this big list. Don't worry about those. This is actually all I want you. I just want you to know these four main categories for now. And you're going to revisit them. You weren't quite here for like my big explanation on like how Sochi works, but it's just a bunch of circles over and over and over and over again.
Yeah.
Same concept revisited in different ways, and that way like you get to absorb it from like all these different perspectives.
Okay.
This class is like a general overview, so sometimes it feels like we're giving you all the pieces to a watch without telling you how to build it.
Yeah, but it comes together.
Yeah, we're gonna get there. Do you have any questions?
No, honestly, I think I'm good. I asked as we were going,
Yeah, it was great. All right, how'd we do today? 7 pages. Woo. All right. So that is about all I got for you. I'm gonna go ahead and end the call, and I'll see you tomorrow, man.
All right, man. You have a good day, Brad.
All right, you too. See ya.